So, before we start talking about our inverse functions, I want to start out with a refresher on what our trig functions are supposed to be in the first place. So let's bring up the unit circle. So this is where everything for our trig functions start. So we have some angle that we draw maybe like this, some angle theta, and then that corresponds to some point on the unit circle that's just this intersection, and this has some x and y coordinate where we intersect the unit circle. So sine, we remember, takes this angle as the input and gives us back the y coordinate. And similarly, cosine takes the angle and it just gives us the x coordinate. So this is just however we have defined sine and cosine to be. And we remember these conversations about domain and range. We can plug in any number. Any number can be some angle, and we will only get an output in the range from -1 to 1. Well, let's say that I knew that sine of theta was equal to something like the square root of 2 over 2. Let's say I knew this much, but I wanted to figure out exactly what theta is. What is theta? Well, if we look at our unit circle, we can immediately see at least probably the quickest solution that we identify is pi over 4. But it turns out that as much as that solution exists maybe right here on the circle, another solution exists right over here at something like 3 pi over 4. And another solution exists if instead of just going to right here, I actually go all the way around the circle again and end up right back here, aka pi over 4 with its coterminal angle that we get by just adding 2 pi. And similarly, we can do the same thing, 3 pi over 4 plus 2 pi. Well, I can just go around the circle another time and instead add 4 pi or 6 pi to go another time around, or 8 pi, so on and so forth, just being going around the circle again and again and again and again. So if I want to get some function, if I want to get some function that takes the y coordinate and gives the angle, a function that undoes sine, I have an issue because if I try and immediately go backwards, I'm getting so many possible answers. There's infinitely many coterminal angles that I could pick from. So I need to figure out some way of restricting the domain of sine, aka telling myself to only look at a specific range of values so that I erase more than I intend to, so that I am able to just figure out one specific answer for my inverse. Okay. So in order to do this, we can look at the unit circle right here. And if I'm thinking of y values, then on this graph, because the unit circle sits in the xy plane, on this graph, if I pick a y value, so let's just say pick a y value. let's look at just y equals something like the square root of 3 over 2. Well, if I'm looking at the y value, root 3 over 2, let's say it's right here. Well, that means that I can draw this line of all these possible points that have a y value of root 3 over 2. It is this actual solid line. And we intersect the unit circle twice, once here and once over here. Well, I need to look at a specific part of the circle where I'm only going to be picking one of those answers. So I'm going to go ahead and cut myself off to not look at any values past pi over 2. Well, what if I looked at something like y equals negative 1/2? Well, now that y value is about right here. And if I draw this line of y equals minus 1/2, it looks like this. Well, similarly, I'm getting stuff on the left and the right side of the circle. So I am going to not go any lower than this point. Well, if I'm going from 0 to pi over 2, then it only makes sense to go from 0 backwards for this direction. So yes, if we just look at the unit circle as we started looking at it, an angle right here would be 7 pi over 4. But I'm not wanting to look at that line as 7 pi over 4, because then I would kind of jump from looking at angles here at 0, then going backwards, I immediately jump all the way up to something like 2 pi, those values right below 2 pi. I don't want to jump like that. I want to go from 0 downwards. So I want to go to the negative values. So instead of looking at that as 7 pi over 4, we're just going to look at that as negative pi over 4. So the point that I'm trying to make is that we're going to go from 0 up to pi over 2, and from 0 down to negative pi over 2. And that's how we end up restricting the domain of sine. Similarly, let me try and erase. Similarly, as we did this in class, we actually just looked at the graph of sine to try and make sense of this, because the same thing is really happening there as well. So let me try and clear things up. All right, so if we graph sine from negative 2 pi to 2 pi, and if this is 0, this is pi, and minus pi, we remember sine starts in the middle, goes up to 1, down to 0, down to negative 1, back to 0. And then we follow the same pattern on the left side, just like that. Well, if I am trying to only get one input for each output, if I'm trying to make it so that I can always just immediately figure out which exact angle I look at based on my specific output, then I know that for a given y value, for a given output, like right here, if I draw this line, oh, well, there's 2 inputs that match this output. So I'm going to not look any further past this line, because that's when I start repeating values this way. And similarly, when I go to the left, once I hit this, I start repeating values. So I'm not going to go any further to the left than just that bump right there. So if I'm restricting the graph of sine, restricting the domain between these two values, Well, those values are exactly what we pointed out before, minus pi over 2 to pi over 2. And similarly, we have a thing that we do for cosine as well, where if I look at the graph of cosine, it looks something like start up here, go like this. Well, if we go any to the left of 0, we start repeating ourselves. And if we go anything to the right of pi, which is just this right here, we start repeating ourselves as well. So to that end, we restrict cosine from 0 to pi. And tangent ended up having the exact same process as sine did as well, which we went into more detail in class. But the point is that if we want to take a y coordinate because sine of theta equals some y coordinate. If we wanted to go backwards, I needed to look at a specific number, specific range of angles so that I can turn going backwards into a nice function. Well, what do we call a function that is just the undoing or reversing of another function? That's just the inverse function. So sine, which I shouldn't write with theta. So sine inverse of y should be equal to some angle theta. So the inverse is our undoing in that sense. And similarly, we can say cosine inverse of x is equal to some angle theta. But specifically in particular ranges, for sine inverse, we said that's our minus pi over 2 to pi over 2. Cosine from 0 to pi. And if we look at tangent, tangent is actually very nice for what tangent is. Tangent is specifically sine over cosine, so y over x. And tangent is very nice for the graph of tangent because it is exactly one regular period of tangent. So one continuous portion of the graph of tangent. So to that end, these are the normal restricted domains for all of our trig functions. So how can we possibly use these in any circumstance? Well, first of all, we have a way of figuring out stuff from right triangles. So before, if I had some angle theta here, and I told you that this was 3 and that this was 5, we don't really know what the angle theta is. Yeah, Pythagorean theorem tells us a squared plus b squared equals c squared, so we can figure out what a has to be here. And it turns out that a does, I erased more than I meant to, a does have to be 4. But that still doesn't help me exactly figure out what this angle theta is. So how can I figure out an angle? Well, so far we only have one tool, one kind of function that gives an angle as an output, and those would be our trig functions. So I can look at this and say, well, if I pretend I didn't know what even 4 was, if I know that the side opposite is 3 and the hypotenuse is 5, then do I have a trig function that relates the opposite side and the hypotenuse to an angle? Well, yes, if we remember our SOHCAHTOA rule for right triangles, I know that sine of this angle theta should be equal to opposite, which is 3, over hypotenuse, which is 5. Well, if I know that the output is 3 over 5, I want to know the input. What do I use? Well, that is exactly what do I plug in a y value and gives me an angle? Well, that is sine inverse. Just sine inverse of 3 over 5. And while maybe we don't know exactly what this is as a number, our calculators absolutely do. So your calculator is absolutely going to tell you the answer here for what is sine inverse of 3 over 5 equals some angle. Now, the fun thing is that your calculator is smart and it knows based on your setting whether your output is supposed to be degrees or radians. So if you really love your degrees for your right triangles, or the question said find the angle in degrees, then you can figure out exactly, oh, maybe this is 72 degrees. Or your calculator could say something like 3 pi over 4 radians based on the setting that you have. And these 72 degrees is not equal to 3 pi over 4. I just made the numbers up just to illustrate. Your calculator will give you an answer based on the setting that you're in. Great. So the next thing that we can do is maybe start asking some silly, complicated questions about these things. So if we look in the workbook, we see some example, like sine inverse of sine of 3 pi over 4. Well, how do we figure this out? Well, can we simplify this at all? Yeah, I can simplify the inside. I know exactly what sine of 3 pi over 4 is supposed to be. That just turns into root 2 over 2. Great. So now it's just sine inverse of root 2 over 2. Well, I need to point out sine inverse is specifically in this range from minus pi over 2 to pi over 2. So to that end, I know exactly that this is supposed to be the angle pi over 4, because that is the angle in the range from pi over 2, negative pi over 2 to pi over 2, whose sine value is the square root of 2 over 2. So some of these we do look at the unit circle for. Some of them we are able to figure out the exact answer. So yes, sorry. So this just turns into pi over 4. Very good. Well, what if I want to take sine of sine inverse of root 2 over 2? Now, in this case, sine inverse is going to give you some angle theta, specifically the angle theta where sine of theta is root 2 over 2. So this is defined to be the angle theta with this output. So if I just call this theta, then sine of theta is by definition supposed to just be root 2 over 2. So we don't even really have to do any of the math there. It decides to erase the oddest of things when I hit erase. Okay. We don't have to do any of the math there to figure out, well, sine inverse of root 2 over 2 is pi over 4. Sine of pi over 4 is root 2 over 2. Going this direction, it almost just immediately falls out. However, you are also perfectly valid and fine in literally doing the math here, and looking at sine inverse and simplifying that and doing all that. I'm just saying in this case, we didn't have to do all that, but you absolutely are welcome to if that is what makes sense to you. So those are a little bit straightforward, but what if I ask something a little bit similar to the last question, but turns into a very different approach? So let's say I wanted to know cosine of sine inverse of 3 over 4? Well, this means I need to know cosine of some angle because our inverse function gives me an angle. I need to know cosine of some angle, we call it theta, where theta is sine inverse of 3 over 4, which is just defined to be the angle theta, such that sine of theta is 3 over 4. So what do I know? I know that sine of this angle needs to be 3 over 4. So how do I represent this? What can I put this in? And the answer is a right triangle. If I know that theta, that sine of theta is 3 over 4, but I also know that, I don't know why I did a theta for the O there. I also know that my SOHCAHTOA rules hold for my right triangles. So sine of theta is equal to opposite over hypotenuse. But if this is equal to 3 over 4, I can go ahead and call the opposite side 3 and the hypotenuse 4. Well, cosine is what we're looking for. Cosine of theta is what we need. And that is supposed to be the adjacent over the hypotenuse. So all I need to know is figure out exactly what this adjacent side is right there. Well, I know that a squared plus b squared is equal to c squared. So if b is 3 and c is 4, then all I have to do is solve for a here. So 3 squared is 9, 4 squared is 16. So a squared plus 9 equals 16. So a squared is equal to 16 minus 9, which is 5. So a just turns out to be the square root of 5. So cosine is the square root of 5 over 4. And that is exactly the entire answer to the question. It turns out that cosine of sine inverse of 3 over 4 is equal to root 5 over 4. So some of these questions, like 2 examples ago, we were able to kind of simplify and solve the entirety of this just looking at exactly what the outputs are supposed to be. But some of these are not so clear cut, and we end up building a triangle to help us figure out exactly what these are, specifically a right triangle, because we have our SOHCAHTOA rules that help us figure out more context for these relations that happen there. So very good. I think that is the bulk of what we care about with our inverse functions. And by the bulk, I mean pretty much everything, besides maybe recontextualizing some of these examples into different kinds of problems. But anyway, yeah, I don't know how to, I'm not going to do an outro. I'm just ending it there. Bye. Thank you.